Hello, I'm Sue Nelson and welcome to the Planet Earth podcast from the middle of the River Thames in London. And I'm here to find out about the science that stops our major cities from being flooded. Also in this edition, some prehistoric CSI.
I suppose it's the size of a large crow that's been flattened.
Welcome to our 120 million year old roadkill.
More on that story later. Yes, I am in the middle of the River Thames, but not on a boat because I'm at the Thames Barrier to the east of London. And it's one of the largest movable flood barriers in the world and could almost be considered a work of art, as it resembles a selection of silvered sections from the Sydney Opera House or maybe the Guggenheim in Bilbao. It's evenly spaced, though, like stepping stones across the river. And it's run and maintained by the Environment Agency, and I'm with Colin Caron from the agency's South East region. I think it's a work of art. As an engineer, I assume you think this is a work of art too.
I do, Sue. I think it looks really nice. And one of the things that happened during the design phase was they went from a simple engineering design with concrete and not looking very pretty to making it a very beautiful work of art, as you say, that reflects the shimmer of the river.
How many of these stepping stones with these sort of silver wings sticking out of them across the river, how many of these are there?
There are 9 piers, Sue, and 10 gates in between, and 4 main ones. The 4 main ones are each of them 61 metres in length, and they all each weigh 3,500 tonnes, which is pretty hefty.
I know, they're pretty substantial structures, and it's only really when you get here, right in the middle of the river, that you can appreciate the size of them.
Yes, they look pretty big close up.
And how does it actually work?
What we do is we can close the river by rotating the gates to prevent storm surges coming from the North Sea into London.
So we've got one of them right behind you here, haven't you?
That's right.
Sort of enormous long barrier that's in between those silver piers.
It's a big steel structure. It usually sits in the bottom of the river in a groove in the concrete sill between the piers and can be moved through 90 degrees into the position where it stops the water.
So the position it's in at the moment now, it's a little bit like a sort of lock in a canal, isn't it? The side of the Thames that I can look over the gate at in towards the City of London, that currently looks as if it's at the slightly higher level than the side that we're at now.
Yes, this is the side where the water gets higher, and then that side there, upstream towards London, it's lower because the water's going to be prevented from getting there.
What would you call its default position? Is this its default position, or is it the default position when the gates are actually parallel to the river and it's all at one level?
It's normally left in a groove in the bottom of the river, and that allows shipping to go to and fro.
The decision on whether to close the Thames Barrier depends on a variety of data, including information from around the coast. And the UK National Tide Gauge Network was set up in 1953 after storms in the North Sea caused serious flooding further along the river from here in the Thames estuary. The network is based in Liverpool, so I caught up with Kevin Horsburgh from the city's National Oceanography Centre, and we met by the River Mersey to find out more about how the network operates and the importance of monitoring storm surges.
Coastal flooding, which is a big concern because it affects over 1 million people and their households around the UK, need good predictions of coastal flooding, and a storm surge is a really crucial element of that. It's the effect that the strong winds and the low pressure in our typically bad British weather systems have on the sea surface, and it can actually elevate sea level by as much as 3 metres. So if you imagine a very high tide, and then on top of the high tide that you were expecting anyway, you can get an extra 2 or 3 metres down to the effects of the weather, and that's a storm surge.
You work with the Environment Agency and the Met Office in order to produce a storm surge forecast. How do you make your predictions? What contribution does your organisation have?
We produce the computer models that actually forecast the storm surges. We work very closely with the Met Office because in order for the model of the sea to work properly, then you've got to have an accurate model of the atmosphere. So this system is a partnership between ourselves, the National Oceanography Centre, the Met Office and the Environment Agency, who have to receive and deliver the warnings to the public. So we depend upon accurate forecasts of winds in order to drive our computer models of the sea, and it's those which are produced by our organisation that give an accurate estimate of the storm surge up to 2 or 3 days ahead.
How do you know that your predictions are accurate?
As well as producing the computer models, we also measure sea level with tide gauges all around the country. So we look after 44 tide gauges around the UK, and the data from those tide gauges helps us evaluate how well our models are forecasting, so we can test how well they've done and we can make improvements. The forecasters that are sitting on the bench 24/7 around the clock looking at the computer model output can also use the data from the tide gauges in real time to tell whether they think the model forecasts are accurate. So they're a very valuable resource for the actual forecasters.
Now, one of these tide gauges, I assume we've got one along the Mersey from us. What do they actually look like? How do they work?
You can measure the height of the sea in a number of ways. Nowadays we use pneumatic air, so we just release air from a cylinder and that air passes through a nozzle at the bed of the sea, and the pressure that it's released at is exactly the pressure of the water above it, and you can convert that to height, and then there's some sophisticated electronics which converts the measurement of pressure into the sea level. Or you can use radar. So there's a number of ways that you can measure sea level, and most of these technologies are complementary, and some of them suit situations better than others.
So where do the measurements that you get nationally around the country about the tide gauges sort of fit in with testing the accuracy of your storm surge predictions?
The 44 tide gauges all transmit their data in real time, so a forecaster sitting on a bench in the Met Office can see it within 15 minutes of the reading having been made. He can compare that with the predictions that are coming out of the computer model, and that gives him some confidence in the nature of the forecast. So he can agree that the computer forecast is good, or he can modify it. So the real-time tide gauge data, it's vital that it gets there quickly so that the forecasters can use it. But we also use it to evaluate the models every year. We see how well they've done during a big event. If there was a big storm surge, then we'll check the heights that were predicted and we'll compare those against the heights that we measured. So we can use the same data to improve the model and to make better models for future generations.
How is climate change going to affect the frequency of storm surges, if at all?
The latest research suggests that it isn't very much. A lot of work has been put into this. Coastal flooding will change and the frequency of events will change because we know that sea level is rising. So sea level measurements are rising at approximately 2 to 3 millimetres per year, and this is a trend that we expect to continue. So that bit we have to take into consideration. Computer models of storm surges, which have been run for the IPCC, the Intergovernmental Commission on Climate Change, and here for the UK Climate Impacts Programme, suggest that there'll be no change to the future storminess that we'll see around Great Britain, at least. There will be changes in other parts of the world, but here at these latitudes we expect the frequency and the severity of winter storms to be about the same. There's no data that suggests any different, and therefore we would expect storm surges to be similar as well.
The information from your tide gauges is used around Britain. You've said how it's used in real time by the Met Office, but it's also used by the Thames Barrier as well. How do they use it in order to determine whether to open or shut up shop?
The information from the forecasting system is used to forecast flooding and to warn people all around the country, but it's particularly important for the Thames Barrier because the Thames Barrier needs to decide whether or not to shut to protect London, and it does that on the basis of a combination of the forecast from the computer model, the real-time data that it's seeing from the tide gauge in the Thames, and from measurements of the river flow at Teddington. And on the basis of all these pieces of information, a decision is then made whether the barrier should be shut or not.
Kevin Horsburgh from Liverpool's National Oceanographic Centre, which coordinates tide gauge data on sea levels from around the coast and helps determine whether the Thames Barrier closes or not, which is where I am at the moment, although not on top of it this time. Am I, Colin?
No, you're right underneath the river here, Sue. We're under about 13 metres of water.
It's amazing, this sort of tunnel filled with pipes. Let's carry on walking along. So we're actually walking not only beneath the river, but sort of beneath the piers as well, towards the banks. That's
right. We're walking in the tunnels below where the gates normally lie in the bed of the river, and you can see on each side there's fire mains for in case there's a fire, and then there's the power cables, 11,000 volt power cables for the power. I'll steer clear from those, and we'll head back now towards the control centre, which is where it all happens. Yes, that's where we do the forecasting and decision making about whether to close the barrier. Here we are, out of the lift, onto the 7th floor, and into the control room. Oh, it's a lot warmer.
get my hard hat off. A fantastic view up here, sort of windows along three sides of the control room. Plenty of computer screens here with various sort of graphs and information, and a couple of people working just to the left of it. So this glorious view. Now, explain what actually goes on in here and the sort of information that you're using. We've heard from Kevin talking about the tide gauge data, and in fact on the screen in front of you you've got something that says surge residual data.
The surge residual data is how much the weather is affecting the tide. The wind is blowing on over the North Sea. You've got perhaps a low pressure area which actually will raise the surface of the water. And what happens is you get a surge of water, a build-up of water in the North Sea that gets blown down the North Sea and into the Thames estuary. And that's what we're looking for.
Now, you've got several lines on this computer screen, sort of different colours, and it says sheerness. So what is this actually showing?
What this is showing is that the sea at Sheerness, which is down at the mouth of the estuary, is actually rising higher than it should be according to the astronomical tide. There's more water there than there should be, and that's due to the weather. We already experienced outside the strong winds that actually push the water around. This is what we're seeing there, is that the extra water coming up the river that's due to the wind.
So that was unexpected, which is why you've got two lines of the graph, the bottom one being what was forecast, the higher one being what has actually happened. So does this mean you've had to issue any warnings?
Yes, we have actually issued a flood alert today, which has gone up to the western part of the tideway, in the sort of Richmond, Twickenham, Teddington area, because at that point there will be some areas where the water will actually come out of the tideway and start to come along towpaths and so on. So we're warning people that that's going to happen, and people will go out and they'll put in dam boards and things like that to stop their houses getting flooded.
So you're using the information from the tide gauges, you're using astronomical data that you already know about the tides, and what else? What's the sort of final piece of your puzzle?
The crucial bit really for us is the mathematical model forecast, and that's done for us mostly at Exeter at the Met Office, and we get it via our network. And what that shows us is what will happen in the future, the next 36 hours really, as far as how much the weather will affect the tide. Because we need a certain amount of time to actually close the barrier. It takes about 9 hours altogether to close it. So far we've had about 119 flood defence closures, which is about 4 a year on average. And they vary quite a bit. And there's no real pattern that we can see to how many we get. So at the moment, global warming, sea level rise doesn't seem to be affecting us, but the future we don't know.
Thank you, Colin. Incidentally, you can see some pictures from our recording here at the Thames Barrier today on our Facebook page. And to follow the latest news from the natural world, do visit Planet Earth Online. To find both, just search for Planet Earth Online. A remarkable paper was published in the journal Science recently. An international team led by Roy Wegelius from the University of Manchester has developed a new technique that reveals the colour and even the chemistry of fossil birds that are more than 100 million years old. The team used high-powered X-rays to detect trace metals in the fossils and have related these to melanin pigments in modern birds. Unlike other methods, the process doesn't involve damaging the fossils. Richard Hollingham went to meet Roy and see the fossils for himself.
This is a 50 million year old fossil feather.
And it's almost perfect. Very fine. And wispy strands.
This is the kind of thing that we call exceptional preservation. You can see the central shaft, and we can see the barbs that fan out from either side. The preservation is absolutely splendid.
So this is 50 million years old.
That's right.
And you can tell from a fossil with your technique the chemistry, and from that perhaps the colour of it?
That's exactly right. We know that the pigments in our hair and skin bind up with certain metals: iron, calcium, zinc, and copper. Copper is part of the enzyme that actually makes the pigment in our hair and skin and in bird feathers. So we thought maybe by mapping the trace metals we could see if there's some kind of information about coloration. Indeed, maybe the color that you're seeing, this preserved color, maybe that traces back.
That's real.
Yeah, maybe that's real. And indeed what we found is at the base of this feather there are higher concentrations of copper than anywhere else in the sample, much higher than in the sedimentary rock and much higher than in the top portion of the feather. The other thing we're able to do using X-rays, not just map the copper, but also get the details of how the copper is chemically bound. What elements surround it? In other words, does it look like an organic compound or is it a purely inorganic compound? And the thing that we found absolutely blew me away. The copper chemistry in the base of this feather is nearly identical to the copper chemistry in melanin sampled from existing organisms. And so maybe we should go to the other specimen, which is perhaps a bit more exciting.
It's very well wrapped, bubble wrap, and then tissue paper. Just pull back the tissue paper. That is incredible. I suppose it's the size of a large crow that's been flattened.
Welcome to our 120 million year old roadkill. What's amazing about it is that this is the first documented bird with a beak.
Oh, yes. Yeah. And again on here you've got colour. You've got much darker wings than the bones in here, which are almost a bone colour, even though this is a fossil. But again, how do you know these colours are real?
What you can see here is that in the neck region and around the body, there's this very, very dark coloration.
Almost black.
Yeah, that's right, almost like carbon black. And if you look at the flight feathers, which are kind of splayed around to either side of the body, the top has this relatively dark black coloration. And then as we move away in the flight feathers and go further and further away from the body, they get lighter and lighter in color. And what we find is that in the neck region and body region, there's very, very high concentrations of copper. We've also done infrared analyses on these regions, and the infrared spectra look exactly the same as modern-day melanin. We've done structural work. All of this information sits together to tell us that the downy body feathers on this bird were very, very rich in this dark black eumelanin pigment.
So this was some sort of black bird.
That's right. That's exactly right. It's unambiguously, non-destructively, and over the whole organism, we can pull out patterns without having to destroy anything.
Now, I mean, this is fascinating. Is this useful?
There are aspects of behavior and evolution and ecology that were inaccessible to paleontologists until they could start to see color patterning. That tells us an awful lot about camouflage, sexual display, a whole different range of behaviors which you really can't get any kind of clue from just bone material. So it's the soft tissue. So for the paleontologists, it's one of the reasons why they're so interested in this. This really might be able to tell them something about behavior. There are other aspects, and the aspect that I'm actually more interested in personally is the chemistry. I think this is an amazing piece of information. We have organometallic compounds that are preserved over 120 million years. That brings us into this whole region of slow reactions. How does it get preserved? I have some ideas about the fact that copper probably acts as a biocide, which is part of the reason why you get exceptional preservation in these well-pigmented samples. But there's a third thing which puts the two of them together. Color is one thing. Organic preservation and how that maps into designing materials and understanding material degradation, that's fascinating. But we can go even one step further. If we can understand these relatively robust organic molecules that contributed with color, we can probably start to tease out other biochemical pathways that are locked away in soft tissues that no one has looked for before. These trace metals contribute to biochemical pathways. They're still present. We know we can map them. And I think this gives us hope that things besides pigmentation actually become available to us as we study ancient life.
Roy Wegelius from the University of Manchester talking to Richard Hollingham about the colour of fossil birds. Well, I'm outside again now, this time at the end of the Thames Barrier, beneath the control tower, looking out across at the different piers stretching across the river. Colin, we've just heard about how we can learn from fossils millions of years old. How long is this Thames Barrier going to last?
It's a good question, Sue. When we first designed the Thames Barrier, it was thought that with all the movements of land and so on, it would sink at about 6 millimetres a year, which would mean that it would start to erode the safety factor by about 2030, which is not that far away. But we found actually by latest measurements, in fact, we're going to get a bit longer than that, probably till 2070. So I think we're okay for a few years yet.
Well, it's nice to hear that the Thames Barrier is going to be part of the city's landscape for quite a time to come. Colin Carron from the Environment Agency, thank you very much indeed.
You're welcome, Sue.
And we're both shivering here, trying to keep away from the wind. And it's been a very windy but pleasant Planet Earth podcast from the Natural Environment Research Council. Don't forget to visit us on Facebook, and you can also follow us on Twitter. Next time, the best of our audio diaries from the past year, including the amazing bone-devouring worms. I'm Sue Nelson from the Thames Barrier. Thanks for listening.